All right, officially, good afternoon, everybody. Welcome back to Intro to Physics, day 22. Woo! We've made it. Okay, so like I was saying before I started the recording, a couple of announcements and reminders and such things like that. Today is our second to last day, so tomorrow is the last day that we will meet together, which is crazy, but that's awesome. We've made it, which means the school year is very quickly approaching. So that's pretty cool. Hopefully I'll see you guys. Well, I mean, I might see you around campus. I don't know who you are and like what you look like for the most part. But you know what I look like. So if you see me, feel free to stop and say hello. Um, yes.
Hi, Mr. Mora.
Hello. Okay, so there's that. We do have a post test that I need you guys to complete. So just like we had the pre-test at the beginning of our session together, I have a post test that I need you guys to do. And that's for my sake, but also for the sake of the program as a whole, to see if there is value in continuing this kind of summer review session intro to physics type class in the future. So if you could at some point between now and Sunday, if you could hop on to Canvas and complete that post test, that would be very, very helpful. Again, there's no grade associated with how well you do. It's just kind of to see if you've improved at all in your understanding during this class, or if things have gotten more confusing for you, which I hope is not the case, but it can sometimes happen. Different professors teach in different ways. I understand that. Yeah, anyway, that's there for you. It should be published and available to you. So again, if you have time between now and Sunday, I think it's set to close Sunday at midnight or 11:59 p.m. on Sunday. That would be excellent. Okay, so my voice has been on the fritz for the past couple of days. I'm hoping that it will hang in there for this hour that we're together. But there are recordings posted on our Canvas page for Momentum, which unfortunately I didn't get a chance to go through with you guys in person. But those recordings are there for you. Now there is a part there on the Canvas page that says it's like bonus problems or challenge problems, advanced examples in Momentum. So those are just some more advanced examples, typical of what you might see on a final exam type problem or on a unit test, that I didn't have a chance to go through in that recording that I posted. So that's there for you if you want to go through some of those more advanced examples. You're definitely welcome to. But for the sake of this intro level, I didn't put them in the actual notes. I'm trying to think if there's anything else I needed to tell you guys. Do you guys have any questions for me before we jump into the topic of the day?
I'm good.
Okay, cool. Well, today and tomorrow we're gonna do gravitation because I know that there are a good chunk of you who are astro people, but gravitation is also covered in Physics 1. So I wanted to make sure that we hit on that a little bit. And then on Canvas, I'll post the slides for like a course overview. So sort of like a summary slide or two for each of the chapters that we covered together, including definitions and equations and things to remember, sign conventions, that sort of thing. So I'll post those review notes, those review slides on Canvas, so that you can take a look through them. Please let me know if you have any questions about them. But hopefully it will be a nice little summary of like what you'll see, excuse me, in Physics 1. I know some of you are taking it in the fall and some of you in the spring, so save that for your notes. You will probably lose access to this class within a few days of it finishing. So my recommendation to you, if you haven't done so and you want to, is to just download all of the materials, all of the worksheets and that sort of thing, PowerPoints, answer keys, so that you can access them on your own later on. Once your access to this course ends on Canvas, I do not have the authority to reinstate it. So yeah, download whatever you want to, save my YouTube channel. If you want to go back and view the videos. Yeah, okay. Anyway, without further ado, let's talk about gravitation. One moment. Let me get it set up. All right. Can we all see our gravity PowerPoint?
Yes.
Great. Okie dokie, here we go. So I wanted to kind of introduce this topic in a little bit of a different way than I have in the past. Previously, with all these topics, we just kind of like jumped right into definitions and that sort of thing. But I think especially for gravitation, it's really interesting to me personally to see how we've come to an understanding that we have right now. Because we really are standing on the shoulders of the giants who came before us. And that's true of all the topics that we've talked about so far. You know, it's not just, it seems like just kind of oh yeah, like look out your window and notice things and there you go, it's physics. Like, yeah, that's true, but there are a lot of people, a lot of really brilliant scientists who came before us who have made it possible for us to understand so much of the world around us. And yet there's still so much more that we don't understand too. So I think that's really interesting perspective to keep in mind. So here are two quotes that I think are kind of interesting to consider. First of all, we live in a changing universe and few things are changing faster than our conception of it. And then secondly, pick a flower on Earth and you move the farthest star. So that first one is really just to make you check your perspective on things. And that second one pertains to gravity that we'll talk about today. Okay, so just a little bit of context, how we came to our understanding about gravity and how it works. We're gonna hit a couple of key people. Now, these are not the only people, the only scientists who experimented with gravity or made some remarkable discovery in astronomy. This is just kind of the highlights. There are definitely more super interesting people that I just don't have time to cover. Anyway, Aristotle, back in 382 to 322 BC, he created this geocentric model of the universe. So geocentric means that the Earth is in the center, geo-Earth, centric, center. So his idea, his understanding of the solar system, of the universe in general, was that the Earth was stationary in the middle and everything else moved around the Earth. So the sun, the planets, the stars, everything is orbiting around the Earth in perfect spheres. And now that might, to us on this side of history, that might seem like a really kind of silly view to have. But if you think about it, like if you are just laying outside at night stargazing, you do not feel like you are moving, right? You feel like the Earth, you're grounded there on the Earth. It is a firm foundation, it is immovable, and you are just watching the heavens dance around you. So you can see the stars and the moon, you know, the sun, even during the day, you see them moving across the sky. So from our perspective, from his perspective, it looks like everything else is moving and the Earth is staying still. So I know a lot of people tend to hate on these geocentricers. I don't know what you'd call them. But like just observationally, you know, for the casual observer, it makes sense. It's understandable. Okay, so next up after Aristotle is Ptolemy. He lived from 100 to 170 AD. And he realized that there are a couple of things about Aristotle's geocentric model that didn't quite pan out, didn't quite fit that model. For example, retrograde motion. So he noticed that the planets, you can see it especially with Mars, but the planets, as they would go across the sky, would sometimes look like they would orbit backwards and then go forwards again. So that kind of backwards motion is called a retrograde motion. So it would move forward and then backward and then forward again across the sky. And all of the planets do that motion. They have that motion. So he thought, all right, maybe the best way to explain this is that the planets themselves are kind of orbiting around, going around in circles as they orbit around the Earth. They're kind of spiraling. And so that spiral motion is called epicycles, these smaller circles that move in a larger circular path. And so just looking at the motion of that, it would show that sort of retrograde forward and forward and backward motion. So he thought, all right, this might be, a plausible explanation of why we see this motion as they are rotating or orbiting around the Earth. Big jump in history to Copernicus in 1473 to 1543. He decided that, really in science, the simplest answer is usually better, is usually correct. So we don't want to complicate things in nature in order to explain them. We want to come up with the simplest explanation. And so he developed this heliocentric model of the solar system. So he said, maybe Earth is not at the center of the universe. Maybe the reason why we see the motion of the planets moving back and forth is our perspective as we also are orbiting around the sun. So heliocentric means the sun, helio, is at the center of the solar system. So the planets and everything orbit around the sun. And you can see in his diagram here, the moon does still orbit around the Earth as it's orbiting around the sun as well. Now, he still had perfectly circular orbits, but you can see we're getting a little bit closer to our current understanding of the universe. Next up, Galileo Galilei, 1564 to 1642. He said, well, maybe we don't have a perfect geocentric universe, right? Kind of agreeing with Copernicus up here. We don't have a perfect geocentric universe. And he supported his position with this using his telescope. Now, I say his invented telescope. Really, he didn't invent a telescope. But he was one of the first to use a telescope for the purpose of astronomy. Because if you think about it, navigators on the ocean, they had things like spyglasses and that sort of thing previously, but people didn't use them to really observe the heavens. So using his telescope, he excuse me, he had discovered 4 moons orbiting around Jupiter. So since there are moons orbiting around another planet, then clearly we don't have a perfect geocentric solar system, because these moons are not orbiting around the Earth, they're orbiting around Jupiter. So he was also the first to discover that objects are pulled to the center of the Earth. He didn't call it gravity, but he discovered that sort of tendency. And he discovered that Venus has phases, kind of like the moon has phases. So all supporting arguments for this heliocentric model. Tycho Brahe. Now, here's an interesting dude. If you don't know anything about him, it's wild. Okay, so Tycho Brahe, he lived from 1546 to 1601. He, again, very, very interesting guy. He wasn't really a theorist. he was more of an observationalist, I guess. So he made the most precise celestial observations possible at the time. So he had created his own observatory, with all kinds of gadgets and instruments and that sort of thing. And he just took incredibly precise measurements of positions of stars and planets and the moon, and how these things all moved around the sky. So astrometry is that's what it's called. And so he just took data. Like that's really all. He didn't try to come up with any explanations for things. He just collected data. But then he hoarded this data. He didn't really want to share it with anybody. So yeah, just super okay. Just a couple of quick highlights about his life because he's just mind-boggling to me. So one time when he was in college, he got into a duel with another student about who was a better mathematician. And then he ended up losing the tip of his nose in that duel. So then he replaced the tip of his nose with a brass nose. And so he just had like this brass nose for the rest of his life because he wanted to prove that he was a better mathematician. That I don't understand that mindset. But anyway, that's kind of interesting about him. He also kept an elk as a pet, which is kind of fun. And then his death is sort of mysterious. Okay, so we know that he like hoarded all of this data. He didn't want to share it. He did have this sort of intern come work for him, who was, he was more of a theorist. He wanted to try to figure out laws of the universe based on data. And so he really wanted Tycho Brahe's data, but Brahe wouldn't share it with him. And so surrounding his death, there are a few conspiracy theories. One is that this intern killed him for his data. Because after Tycho Brahe's death, all of this data was just like mysteriously put into the possession of this intern, who then created all kinds of really famous, important laws based on this data. So that's kind of sketchy. Okay, so that's one theory surrounding his death. But while he was still alive, he created this model that he thought made the most sense from his data. So it kind of combines, I call it a hybrid model. It combines heliocentric and geocentric. So the sun orbits the Earth, but everything else orbits around the sun, right? So all the other planets are orbiting the sun, while the sun orbits around the Earth. So kind of in a way, everything orbits around the Earth, but the Earth is not at the center. It's strange. Again, in astronomy, well, in science in general, the more you complicate things, likely the farther you're getting away from the truth. So nobody really adopted this model. It was just kind of like hey, here's a potential explanation from a non-theorist. Okay, but anyway, back to his death. He was so concerned with his image. He was pretty like noble and invited to a lot of important parties and stuff. So one idea was that he was at a party and he liked to drink. And so he may have drunk so much that he really had to pee, but it was very rude to get up before your host or hostess kind of got up from a party. And so rumor has it he just held his pee so long that either his bladder exploded or got a bladder infection from just refusing to be impolite at a party and going to the bathroom. One idea was that he was poisoned by his brass nose. And then, yeah, a lot of people thought, well, maybe he was murdered or poisoned by his apprentice, his intern. And that intern turned out to be Kepler, Johannes Kepler, 1571 to 1630. So if you have taken any astronomy class, you've probably heard of Kepler's laws, because again, he took all of Tycho Brahe's data when he died and he used it to create these laws of planetary motion. So his 3 laws of planetary motion, we'll go into more detail about that later. But basically, he said that the orbits of the planets are not perfect circles. They are actually ellipses or kind of ovals, not super elongated. This picture greatly exaggerates things, but they're not perfect circles. They're slightly elliptical. And that actually solves all of the mathematical problems that people were having with these circular models that they could not explain. So this did away with all of the epicycles, circles within circles. It just simplified everything.
Oh, what about Kepler's perfect solids and him trying to explain the orbit, the orbited I can't say it, but like trying to explain like the orbit of like the planets in that way.
I don't really know much information about that, so I can't really say anything about that.
Oh, okay.
But that's cool. I'll have to look into that. Okay. So Isaac Newton, of course, we've heard about him in the past. He just does everything in physics. So 1642 to 1727, he did not invent gravity. He did not discover gravity. What he did was really just expand on Galileo's ideas of how everything falls to the center of Earth. He kind of took that idea and extended it into the universe, into things away from just the Earth as well. So what he did discover is that gravity is universal. He's credited for discovering gravity, but really he didn't. He just discovered that it's everywhere in the universe and that it affects everything in the universe. Okay. So the way, I mean, the popular story about this, if you haven't heard it, is that he was like sitting in his garden under a tree, looking up at the moon, and an apple fell on his head, and he was like, "Oh, gravity." So there might be like some grains of truth to that story. Maybe, he did find a similarity between an apple falling down to the earth and the motion of the moon. But here's kind of the logic behind his universal gravitation discovery, right? So let's say he looked at the apple falling and made that observation that it falls straight down to the center of the earth unless it's impeded by something. So if we look at the moon, right, we know that the moon is moving around us. And so if the moon, here we go, if the moon is orbiting around us like this, in a sense, it's almost falling down towards the earth, right? So if the moon didn't fall in its orbit, then it would follow a straight line path, right? So think about circular motion, right? If it didn't fall, then it would follow a straight line path and just go out into the universe indefinitely, right? But that's not happening, right? It's being attracted to the earth. Something is pulling it into the earth. So as it falls, it follows this curved path around the earth. It does not fall straight down towards the earth, fortunately, because it is moving tangentially sideways around us. But it is kind of falling down around the earth. So to put this into a little bit of like an easier perspective to understand, let's say you're trying to throw a rock on the earth, right? So here you are at the top of a very tall building and you're going to throw a rock. So if you just throw this rock with only a little bit of speed, it'll go a little bit of distance and land kind of right in front of the building. If you throw it a little bit harder, it'll go a little farther before it lands on the ground in front of the building. And so the harder, the more force you put behind this throw, the more speed you give it initially, the farther it will go in it before it hits the ground. Now, if you could throw it so fast that it misses the edge of the earth completely as it's falling down, you will have put it into orbit. So that's basically what we try to do with rockets. We try to give them enough speed so that when they fall back down towards the ground, they end up missing the Earth completely and are put into orbit. So we got to find that right speed, that high speed that allows it to keep missing the ground, right? So as it falls, trying to hit the ground, it's going to keep curving around and around and try to hit the ground. But in the absence of air resistance and friction and those sorts of things, it will just keep fall forever around the Earth, and that is orbit. So he said, this is what the moon is doing. It is just continually falling around the Earth because it has some sideways velocity to move it sideways enough to miss the Earth when it falls. So that's called tangential velocity. That sideways or parallel to the Earth's surface velocity. And so he said that the planets must orbit the sun the same way the moon orbits the Earth, right? They just have enough speed as they go around the sun to miss the sun as they try to fall towards it and end up kind of rocketing around in this orbit. They have enough tangential velocity. So what would happen if the tangential velocity of Earth, for example, as it moves around the sun, what would happen if the tangential velocity is decreased to 0? Well,
The moon,
yes,
that
Vic,
means
sorry, Victor raised his hand. I saw the little icon come up.
Would it be that the sun's gravity would just pull Earth towards it?
Yes, absolutely. The Earth would fall right towards the sun, right? So if the sideways portion of its velocity was 0, then there would be nothing to carry it around, missing the edge of the sun as it falls. So it would just go right towards the sun. Bad day, right? What would happen if the gravitational force or that attraction of the sun was decreased to 0?
that means things will start floating away.
Yes, exactly. They would just fly off into space in whatever direction they happened to be going when gravity turned off. So either way, that's a pretty bad day. If you're plummeting straight towards the sun, that's a bad day. And if you're flying off randomly into space in some direction, that's a bad day. So the fact that we are in orbit around the sun means that we have a pretty delicate balance. It's kind of like a dance, like a well-coordinated dance between the tangential velocity and the force of gravity. Okay. So coming back to this idea of inertia, which was covered in Newton's laws, he incorporated this idea of inertia, or the tendency of an object to keep doing what it's already doing, into his first law of motion, right? Which tells us that if there's no outside force, no unbalanced force, then an object that is moving will keep moving at a constant speed in a straight line indefinitely. So if an object changes its speed or its direction, then that was because there was some force that acted on it. So if we think about the moon is not following a straight line path, right? Because if it were, it would be just rocketing away from us. So it circles around the Earth. And that means it's constantly changing its direction. So there must be a force acting on it. Revisiting this idea of acceleration, there are 3 different ways that you can accelerate an object. Do you guys remember what those are? Yeah, go for it.
Increasing the mass.
Not that one. Increasing something.
Change in velocity?
Yes. So we can change the velocity 2 different ways. Right? You can speed up or slow down. What is the other way that you can accelerate an object? Kind of embedded into velocity as opposed to speed.
Change in position or direction?
Change in direction, that's the one, right? So if we speed up or slow down the object or change its direction, any of those would be a change in velocity. Remember, acceleration is how velocity changes over time. So if any of those aspects of velocity is changing, the magnitude or the direction, then we have an acceleration, right? So speed up, slow down, or change direction, right? So the moon, as it's orbiting around the Earth, is constantly changing direction. So there has to be an acceleration then. By definition, that is an acceleration. And according to Newton's second law of motion, if there is an acceleration, then there is a force. Force equals mass times acceleration, right? So if we change the motion of an object, that means that there was a force acting on it. What is that force? Well, Newton figured that that force is the same for the moon falling towards the Earth as for an apple falling towards the Earth. And they fall for the same reason, and that's the Earth's gravity. So it's this gravity that is pulling on both the apple close to the surface of the Earth and the moon way far away from the surface of the Earth. Gravity is changing the motion of those objects in either case, regardless of whether it's close to the surface or far away from the surface. Okay, so according to Newton's second law that we have been using pretty regularly since we learned about it, force equals mass times acceleration, right? So force of gravity equals mass times g, acceleration due to gravity, right? Well, yes, up until now, because we've only been considering things that are close to the surface of the Earth. But when things get far away from the surface of the Earth, our equation changes a little bit. So now we have to consider not just the mass of the object that is moving, but also the mass of the Earth, how far away the object is from the Earth. And so it gets a little bit more complicated. So here's our new equation for the force of gravity. Force of gravity equals capital G times m1 times m2 divided by r squared, and it acts towards the gravitating body. So looking at this equation, this is called Newton's law of universal gravitation. This law applies pretty much anywhere in the universe, including near the surface of the Earth. Okay, so the direction is important because it's a force, which means it's a vector. So the fact that it's towards the gravitating body or towards the more massive body, that is important to consider. Okay, so this capital G in here is called Newton's gravitational constant, or a lot of people refer to it as big G. And so this number in yellow is an important one to memorize or have written down on your equation sheet. This is a constant, just like 9.8 meters per second squared. You'll use this constantly throughout these problems. So 6.67 times 10 to the negative 11 meters cubed per kilogram squared. That is our gravitational constant, big G. Okay, mass 1, mass 2 are the masses of each of the objects. So not only do you consider the object that's falling, you also consider the mass of the object that is causing it to fall, both in kilograms. So sometimes you'll see this equation written as capital M and lowercase m for the bigger mass and the smaller mass. Same thing. And then R is the distance between their centers in meters. So this distance is not from surface to surface, it is from center to center. And that is important. So according to Newton's third law, right, that action reaction law, for every action is equal and opposite reaction, gravity on the moon by the Earth, so that gravitational attraction that the moon feels from the Earth, is the same as the gravity on the Earth by the moon, right? Those two forces are equal to each other, opposite in direction. The moon is pulling on the Earth just as strong as the Earth is pulling on the moon, just in opposite directions. And it's going to affect the motion of the moon more because the moon is much less massive, so it has less inertia, and it's easier to change the motion of the moon than it is to change the motion of Earth. Okay, so for any pair of objects, that statement is true. The force of gravity on the Earth from the sun is the same in magnitude as the force of gravity on the sun from the Earth. It's just that since the sun is so much more massive, it's much harder to move the sun or to change its motion than it is to change the Earth's motion. Okay. Now, the force of gravity is an extremely weak force. I know it feels strong because, like, we are on Earth. Earth is holding us onto it. It's, you know, kind of critical for life as we know it. But it's actually an extremely weak force, right? You can jump and fight against the force of gravity. So we only really sense the force of gravity when masses like the Earth are involved. Because if you think about it, my computer right now has mass. I have mass. And so my computer and I are gravitationally attracted to each other. And yet my computer is not actually like moving towards me in any perceivable sense. So we only really sense it with these big masses, right? And that's because we're so close to the surface of the Earth. And so the Earth's gravitational pull is much stronger than mine is. So my computer is more attracted to the Earth than it is to me. Okay. So take a look at our equation for gravity now and think about this example. Sedna is 3 times farther from the sun than Eris. Assuming Sedna and Eris have the same mass, dwarf planets, compare how much gravitational force each gets from the sun. Okay, so take a second, think about how this information applies to our new equation for gravity and what our potential answer might be. Then we'll think about it together. All right, so that was just a little bit of time to think about it. I didn't give you a ton of information, but I did give you plenty of information to answer this question, right? We didn't need to know the masses of these two objects in order to answer this question, because we're just comparing, so like relative to each other, how much gravitational force they get from the sun. The only thing that really matters to know here is that distance. So the fact that Sedna is 3 times farther away from the sun than Eris. That means that Sedna gets 1/9 the gravity that Eris does, right? And that's because our distance here in the denominator is squared. So if Sedna is 3 times farther, that's 3 squared. So that would be 1/9 the force of gravity. Okay. So this is called an inverse square law. And that means that distance dramatically affects the force of gravity. Okay, it drops off with an inverse square law. And on a following slide, I have a graph of what that looks like as an inverse square law. So here we have again our equation for the force of gravity, but we know from Newton's second law that force equals mass times acceleration. So if we plug that in here, mass times acceleration equals g times m1 times m2 over r squared. And that way we can cancel out one of the masses. So the mass of the little object, for example. And so we get the acceleration equals g times your other mass over r squared. So here's our equation for acceleration due to gravity now. Okay, there's a question in the chat. How do we figure out the sun then? Can you kind of explain your question a little bit better? Does that pertain to this slide or the previous slide? The previous slide. Okay, one moment, let me go back. Okay. So how would we figure out the sun then? You mean the exact gravitational force from the sun? Okay, if we wanted to figure out the force of gravity of the sun. So in that case, you would need to know the mass of the sun, which we weren't given in this particular problem. So since we weren't given the masses, we can't calculate the exact value of the force of gravity. We just know that compared to each other, the force of gravity on Sedna is much less than the force of gravity on Eris because it's farther away from the sun. Now we will do some examples where we do figure out the force of gravity of some certain objects. So I'm going to put a pin in that question and go through some of our examples. And then if you still have a question about that later on, remind me at the end of class and we can talk about it. Sound okay? Okay. So our acceleration here, we know is due to gravity because that's what we're talking about right now, right? Gravity. So our acceleration can really be written as g, lowercase g. Right? So our acceleration due to gravity is this universal gravitational constant times the mass divided by r squared. So that canceled mass, which mass we canceled out, it doesn't really matter. We still will end up with this result for our equation. Okay, so here we go. Here's example 1. What is the force of gravity on an astronaut on the International Space Station? The International Space Station orbits at 405 kilometers above the Earth. The Earth has a radius of 6,371 kilometers and a mass of 5.97 times 10 to the 24 kilograms. Assume the astronaut is 75 kilograms. Here's our value for G. How does this compare to the values on the surface of the Earth? So we want to know, basically, is there more gravitational force on this astronaut in space, in the International Space Station, or on the surface of the Earth? So I want you to kind of guess before we calculate it, make a hypothesis. Do you expect it to be more or less than just her weight on the surface of the Earth? Right, so this astronaut on the International Space Station, do you expect her weight, her force of gravity, to be more or less than on the surface of the Earth? You don't have to share your answer, just make a prediction. Okay, so here's our equation for the force of gravity. And there's our astronaut on the International Space Station. So on the surface of the Earth, we know already how to calculate her weight, right? The force of gravity is weight. So that's just mass times little g. 75 kilograms is the astronaut's mass times that acceleration due to gravity, which is 735 newtons. Now we can check that answer using our new equation for the force of gravity, big G times m1 times m2 over r squared. So big G here is 6.67 times 10 to the negative 11. Mass 1 is the mass of the Earth, 5.97 times 10 to the 24 kilograms. And mass 2 is the mass of the astronaut, 75 kilograms. The distance between them, remember, these distances are from the center of the Earth. So even though the astronaut would be standing on the surface of the Earth for this part, that's not a distance of 0 anymore for this equation. That's a distance of the radius of the Earth. So that's the 6.371 times 10 to the 6 meters. We need this distance to be in meters, not kilometers, because if you take a look at the units for this gravitational constant, it has meters embedded into it. So we need distances in meters and we need masses in kilograms in order to use this as our value for the gravitational constant. Okay, so that's why I converted that to meters here. And then we need to square that because it's radius squared, or the distance between the center squared. So compared to the radius of the Earth, the radius of the astronomer is pretty inconsequential, right? So we don't really need to consider that in our equation here. But we end up with a value of 735.8 newtons. So very similar with our, not rough approximation, but alternative equation, I suppose. We end up getting very similar results here. Okay, so on the surface of the Earth, both equations are equally valid to use. Okay, and we're using here that G equals 9.8 meters per second squared. So now if we consider the astronaut while he's on the International Space Station, we have to change the radius now, because we're not just thinking about the radius of the astronaut himself, like on the surface of the Earth. But now this astronaut is above the surface of the Earth by 405 kilometers. That's a pretty significant value, even compared to 6,000 kilometers. So our new distance from center to center is the radius of the Earth plus that height above the surface of the Earth. So 6,776 kilometers. And remember, we want that to be in meters. Otherwise, our answer will be off by a factor of 1,000,000, which is significant. So we need to convert our units here to meters. And now we can consider our equation. So big G, 6.67 times 10 to the negative 11. Mass of the Earth, 5.97 times 10 to the 24 kilograms. Mass of the astronaut is 75 kilograms. And here's our new distance between them. And you'll see we end up with 650 newtons. Right, so previously we had a value of 735. So this is less than on the surface of the Earth. And if we were to calculate our new acceleration due to gravity at this location, remember that equation is capital G times the mass divided by the radius squared. So our acceleration due to gravity from the Earth is G times the mass of the Earth divided by that distance between them squared. We get a new acceleration due to gravity at this location of 8.67 meters per second squared. So no longer 9.8, it's 8.67. Okay. So this kind of proves that astronauts are not weightless in space. Right? A lot of people say that they are weightless. Technically, like according to the technical definition of weight, they are not, because weight is the force of gravity, and they have a force of gravity. So really the reason why astronauts float around in the International Space Station is not because they are suddenly weightless, because that would imply that they suddenly have no mass, which is problematic, or that there's no gravity, which is problematic, because again, if there's no gravity, then we would just fly off randomly into space, which is not happening. So there is gravity in space.
Oh, fun fact, the space station is in low Earth orbit.
It's true. Yes. So the reason why astronauts float around in the International Space Station is just because they're falling at the same rate as their surroundings. So just like the moon falls around the Earth, when it's in orbit, the International Space Station is falling around the Earth and it just keeps missing it. And the astronauts inside of it are falling around the Earth at that same rate because they're in the same location, the same altitude above the surface of the Earth. And so they're just falling at the same speed as their surroundings, right? Same thing would happen if you're like, in an elevator in a super tall building and the cable breaks and the elevator is just plummeting down towards the ground. You are likewise plummeting down towards the ground. You would be experiencing a similar sort of feeling as an astronaut, right? And astronauts, as they train, They go in what they call the vomit comet, which is just a plane that goes up and down in these parabolic motions. And so as it goes up, the astronauts can experience the force that they might feel, well, a similar force to take off or blast off, or the rocket launching, right? And then as it plummets down towards the ground, they are falling at the same rate as the plane. And so they can float around and get that sort of sensation. There's a comment in the chat. They're moving surprisingly fast around the Earth. Yeah, they definitely are moving surprisingly fast. So it takes the International Space Station about 100 minutes to orbit the Earth once. Like, just let that sink in for just a quick second. Like 100 minutes to orbit the Earth. Like, that's wild. It takes the moon about 27 days to orbit the Earth once. So that's crazy. It's just super fast. Okay. Anywho. So here's this graph that I was showing you about this inverse square law. So we can see that as we get farther away from the Earth, this force of gravity quickly drops off. So this is an inverse square graph, right? And you can see just how important the distance is from the object when you think about the force of gravity acting on it. Okay. Okay, we have a couple minutes left. We're gonna keep on checking for the last couple minutes. So acceleration and velocity. So here are some equations. Some of them may be familiar to you. Some of them might be different. We didn't get a chance to go through rotational motion together, which corresponds to orbital motion, right? But here, some of these are rotational motion equations. So we can figure out angular velocity, or the rotational velocity, which is given this lowercase omega symbol. That's the change in the angular displacement divided by the change in time. Okay, so how far it's moved around the circle, around its orbit, is the angular displacement. Centripetal acceleration, this is the one that we had seen previously in another example problem. Centripetal acceleration is velocity squared, or tangential velocity, linear velocity squared, divided by the radius of the circle, which is the same thing as the radius times angular velocity squared. The period is how long it takes to go through a complete orbit. So you need to know the circumference of the circle, right? Because that's the complete orbit, the distance of the orbit, which is 2 pi r. And you need to know how fast it does that. So you need to know the velocity, the speed. And so the distance divided by the speed gives us the period, or the amount of time that it takes for the orbit. And then we saw this one previously on another slide, acceleration due to gravity. Okay, so here is our second example, and we'll end at the end of this example. We want to find the radius of a satellite that takes 24 hours to orbit the Earth. So at this location, this is called a geosynchronous orbit. Geosynchronous means that it is always lined up with the same location on the Earth. So something that is between the International Space Station and the moon could take exactly 1 day to orbit once, right? If the International Space Station takes 100 minutes to orbit once, and the moon takes 27 days to orbit once, that means that somewhere between those two, it would take you exactly 1 day to orbit around the Earth. So these geosynchronous orbits are commonly used for communication satellites, so that they seem to like hover over the same place on Earth all of the time. Now, I didn't get a chance to look up this fact for this year, but as of today, last year, there were over 29,000 satellites. So that would be larger than 10 centimeters. that are in orbit around the Earth, 7,389 artificial satellites, and about half of those are active. Just a fun fact. Anyway, so remember the mass of the Earth, we saw that in example 1. The radius of the Earth, we also saw in example 1. So we need to remember what the direction of acceleration due to gravity is. And remember that the gravity always pulls in towards the center of that massive object. So inward toward the center of the circle means it is a centripetal force. It pulls in towards the center. So gravity is a centripetal force. So that means that the force of gravity here, our equation for the force of gravity, we can equate to centripetal force, which is mass times centripetal acceleration. And centripetal acceleration we saw on the previous slide is r times omega squared, which is our angular velocity squared. Angular velocity is the change in angular displacement over the change in time. So that's 2 pi radians. It'll go around 2 pi radians, which is a complete circle, in 24 hours, which is 86,400 seconds. So that means that it is moving at a speed of 7.269 at times 10 to the negative 5 radians per second. Okay, question in the chat. What's the difference between a satellite and an artificial satellite? So any like rock, space debris, rock, that is larger than 10 centimeters is referred to as a satellite. I mean, anything that orbits the Earth or orbits a planet or orbits anything is called a satellite. So artificial satellites are specifically ones that are man-made that we have launched. Okay. Okay, so therefore, we have our force of gravity here, equating it to mass times centripetal acceleration. Right, so we can see that there is a little m, a little mass on both sides that will cancel out. There are r's on both sides. They will combine. They will not cancel out. And so if we rearrange this equation to solve for the radius, we get big G times big mass divided by the velocity squared equals the radius cubed. So if we take the cube root of both sides, we end up with a radius for our geocentric orbit of 42,240 kilometers. Okay, so this would be the location that we have all of those communication satellites, etc. And this includes the radius of the Earth too, right? Like this is the distance from the center, not from the surface. Okay, do you guys have any questions about this portion of gravity?
Could you please go back to the previous slide?
I can. Okay,
Thank
so
you.
tomorrow in class, we will do some additional important equations to consider for gravitational motion, like escape speed and orbital speed and Kepler's laws of motion, that sort of thing. So we'll wrap up gravity tomorrow, and that will wrap up our time together. So like I said at the beginning of class, in the beginning of this recording, please take some time and do that post test that is posted on Canvas. It should be available to you. If you have any problems viewing the pictures that are in it, just send me an email and I'll try to get that figured out. But it is there for you, and it needs to be done by Sunday night at 11:59 p.m.
Miss Zamora,
Yes.
I have to go.
Okay.
You have a great day.
Thanks.
Thank you,
So
Professor.
you're welcome. So please do that post test. And I will see you guys tomorrow. Have a great day.
Thank you very much. Have a great day.
Thank you.